Good. So today, or rather, Monday, I was a little ambitious. I said we'll be able to wrap this chapter up by the end of this week. I don't think we'll make it, and this is a delicate balance to walk, because I do want to get to where I want to get, but I also don't want to lose all of you, because otherwise, what's the point? So I have to walk this very delicate line. So we're going to slow down a little bit. I'll revisit a couple of points that we were doing that we kind of jumped over on Monday, and then today we'll talk about the uniqueness theorem and what it implies. There's a lot of math involved there, and this author of the book has obviously has all of that stuff really in his fingertips. So he'll throw out stuff like, oh, obviously this is true and that is true, which is fine. But I do think that some of those things could use a little bit more elaborating. So we'll do that, and hopefully we'll wrap up the chapter on Monday next week. So having said that, there are a couple of calculation points that I want to note. We did not talk about contour integration as a math review, and that's not because I don't like contour integration. I think it is a fantastic invention, and I think it's super useful. And you'll see it a couple of times in this book. But I don't think that's necessarily a physics course. So it's not a course in mathematical methods, even though I know sometimes it feels like it. So, and of course, the boundary between what is math and what is physics becomes a little hard to draw when we have to really crunch through a lot of math to get to the physics. So whenever there are things that I think this is really no longer in the part of the part of physics, it's more math, then I'll usually just say, okay, this is the integral and this is the outcome. So let me give an example. So when we were doing the review on Fourier transforms, I gave you the one-dimensional harmonic oscillator. I said, well, how would you solve this equation? And all I wanted to know at that point was I wanted to see that you all knew how to that you could use a Fourier transform to make this into an algebra problem, and then all you needed to do find the appropriate inverse transform and then write it as a convolution integral. And then from that point, you have taken this problem, thrown it around a little bit, and then you wrote it like a single expression for x as a function of t, which is equal to something on the right-hand side. And that something on the right-hand side sometimes can look quite complicated. And I think at that point, it's no longer super useful to be able to execute that integral, because then you already have your answer. You know what I'm saying? And so I'll try to keep that approach, because I do think that otherwise we sometimes get bogged down in details a lot. And that's one of those integrals that I myself, I never know by heart, but I do know how to get there to the point where it's an integral and you can plug it in Mathematica or whatever it is that you're using. Okay, so I hope that's going to speed things up a little bit without skipping over too much of the details. All right, here we go. So so towards somewhere like 3/4 of last class, we encountered this setup where we looked at a charge distribution rho that was only a function of r, so only a function of r. So in other words, spherically symmetric, so no theta or phi dependence. And then there was an expression for the potential that showed up, and let's make sure that we know where that expression comes from. So let's take back a step. So I'm going to walk through the exercise that is on the book. Let me see, page. Where are we? 13.1 and 13.2, and then afterwards you should be able to do the other one. So the 13.1, my book go. 13.1, we're talking about a basic example of a spherical charge distribution. We have a uniformly charged thin spherical shell, so thin charged shell with charge Q and radius R is the radius. So very basic problem. So we have this coordinate system. This is our sphere. This is when I got to draw circles again and really impress all of you very much. All right. So this is our sphere. That's our big radius R. It's got some charge Q sitting on the surface. So find E and then phi. So as a function of R, E of course is a vector field. So Gauss's law, you know, says that E dA, it's whatever Q is enclosed. All right, and there's a 4 pi here somewhere. Yes, I believe it's like this. Yes. That's one of those things that I do this in SI units so often that I don't know where the 4 pi's go. I think this is right, but we'll see. Okay, so the idea is that there are two solutions to this. There's one where you're evaluating the field outside, right? Because this Q enclosed is whatever is within your Gaussian surface. So let's say we pick two Gaussian surfaces. There's a blue one and a red one. So let's do red first. Ooh. So this is where R is bigger than R. So in that case, your integral is just 4 pi R squared times E, because that normal, that dA is pointing out. This should be comfortable territory. So that's your 4 pi R squared E. And then your enclosed charge when your R is bigger than R is 4 pi, just whatever total charge is Q. And then therefore you get the field in the red situation, which is Q over R squared. And of course, because it's in the R hat direction, you know, radially out, there you go. So that's your red field. Now, when your Gaussian surface is inside, so this is your R is less than R, then you still need to do your 4 pi R squared E, but now of course your enclosed charge is 0, so your blue field is 0. The book doesn't really write 0 vectors. I like writing 0 vectors, even though of course there should be no doubt what the components are of a 0 vector. So that's your 0 vector. So red field, blue field. So now your potential in general is going to be minus the line integral of E. Oops, I don't know when I'm writing A, EDL. And of course, because your field is not changing in any other direction other than R, and also it's only pointing in the R direction, we're going to be integrating over the direction R. And we're going to start at the point infinity, and we'll end up in some point r, where we want to know what the potential is. So that's the potential. So and we're integrating over this. All right, that's your potential. And then if r here is bigger than r, then that means you just do minus the integral r, oops. And then E is Q over R squared. And then we're going to integrate that over dr. Okay, so that's your 1 over R, Q over R, to R. And that's an R prime if you want to be. I never confuse R and R prime, but if you want to, you could write this as R prime. So that's your potential, Q over R. Now, when you want to know, so that's the potential in the red zone. If you want to know your potential in the blue zone, you do the same thing. So you start at infinity and you end up in some point r of E that you dot with your dr. But of course, E is 0 as soon as you hit big R. So in other words, this thing is going to terminate at big R. And then it's the same integral because the field outside is just the field outside. And you'll end up with, instead of Q over little r, you'll end up with Q over big R. So that's your potential in blue. Okay, so let's make this problem a little bit more interesting. So instead of, and that's actually the subject of 13.2. So so now it's a uniformly charged sphere. So uniformly charged sphere. So still with the radius big R. Now, for the red part of that field, it looks exactly the same, right? Because it only cares about what the total charge is that's enclosed. So still your red field, so E for R bigger than R, is still going to be that total charge Q R squared R hat. Now, inside is a little bit more tricky. You need to do a good job of your bookkeeping. So you have your E dA is your Q enclosed. So in other words, that's your rho dV. Let me see if I'm not mixing up my 4 pi's. Yeah, might be missing something here. Let me see. No, I think there's a 4 pi here. Anyway, otherwise we'll fix it. So inside this E field, it's going to be E times 4 pi R squared, and rho integrated over the volume would be the same volume that this thing is around. So you'll get the integral of rho times dV. Yeah, I think I have an extra. Okay, so this is 4/3 pi little r cubed. And then that times your charge density rho. Okay, I think I did it right, except my eraser is malfunctioning. Yes. All right, so I think I got that right. Now your rho, of course, is that's your charge density. So rho is the total charge, so that's your Q divided by 4/3 pi R big R cubed, right? So that is 4/3 pi R cubed over 4/3 pi big R cubed. Okay, and then you get your R cubed over R cubed. Yep, there we go. And now, therefore, E, the blue field, is, yeah, there's a 4 pi here still missing somewhere. Yeah, I need to check my prefactors. I think there's still something missing here, but you'll end up with a Q R or R cubed R hat. Okay. Now, when you integrate this potential is still going to be the same, but now this potential is going to give you a quadratic change in potential. So you do the exact same thing. So you split up your potential integral between part in the red and a part in the blue. You'll get still the same red potential. So your phi of R bigger than R is still going to be Q over R. But your blue potential is something different, right? So you do an integral where you terminate first at big R, and then you pick up that Q over big R, and then you evaluate the rest of the integral integrating this field. Okay, so I'm gonna let you work on the Nearpod on the following situation. So we're generalizing this. Now, arbitrary charge distribution rho of R, but let's assume that it's not that it doesn't go to infinity. Okay, so it's bound. I don't know if bound is the right way, but anyway, it doesn't go to infinity. Okay, so we have some rho of R, and it does something. So that's R, and that's rho. And your question is first calculate E of R, and then calculate phi of R. All right, let's see if you see the next step. Okay, so your phi r is supposed to be the integral minus e of r prime, except we're already going to use an r prime. So I'm going to call this double prime, dr double prime. So that's minus the integral dr double prime Okay, so let's go over what we're going to do. So the point of getting a closed expression, actually, let me just walk you through the first part. So arbitrary charge distribution, rho of r, dies out before we hit infinity, so that's okay. So things are not going to be exploding. We are just using Gauss's law in integral form. There is supposed to be a 4 pi here. I fixed that in the notes. So that's your flux, and that's your enclosed charged. So EDA, because it's spherically symmetric, is going to just be 4 pi r squared e. And now this is going to give you a 4 pi from the actual law, and then we're integrating over dr, d theta, and d phi with a 4 pi r squared sine theta. And because there's no theta and phi dependence, that becomes a 4 pi. So we have an extra 4 pi here. And then the rest, we are left with just the r squared rho dr. But now we have to start being a little bit careful with where we're going to put primes, because in the end, we'll have a double integral, and then it becomes really important to do the bookkeeping properly. So, but we do get an expression for the electric field that looks straightforward. There's a 4 pi here, there's 4 pi squared, so we end up with a 4 pi over r squared integral. Okay, straightforward, 0 to r, that's your enclosed charge. Okay, so that's your electric field. Now, the potential is just minus the line integral from infinity back to r of that E dr, and again, we're assuming that E is only pointing in the r direction because we've got spherical symmetry. And therefore, it's just minus the integral from infinity back to r. We put our reference point at infinity because we said that charge distribution is going to go away there at some point, and we'll do an integral over r. But now we already had a couple of r's in the problem. We had the r on the inner integral, that's our r prime, and that's what's going to run until 0 to r. So after you're outside of this integral, we have this function only of r. So this r here and that r, they're the same. And now we are we want to integrate that electric field over R. That means that the variable that you're going to integrate over is that same R that comes out here. So therefore, we replace, we put the electric field here, we replace all the R's with an R double prime, and we keep the R single primes. We could swap the R's, the double and the singles, that's okay. But in the end, it's important that you do your bookkeeping properly. So after this outcome of this integral, we'll have something that depends only on R double prime. And now this expression is an integral over R double prime from infinity to R. And now that's the actual R that is the input to that potential. Okay, so that's all our bookkeeping. Now, integration by parts. I like doing this, writing it this way. This is just a reshuffling of your regular product rule. So you see that we can get rid of one of the integrals by using this rule, right? So we have an integral of fg prime, and then an fg, and then the bounds of the integral that we have here, minus f prime g integrated. But here you see that we have an f prime, and here we have an f, and we have an f here. Now, what if we use as f that inner integral? Then that means that your f, when you take the integral here, you just evaluate whatever you're integrating between the bounds of your integral. So that's how you get rid of your first integral. And then this other part that you're integrating, so your g prime, that will be the thing that is in front. So that's 4 pi over r double prime squared. So that's the derivative. G prime is that. So in other words, g would be minus 4 pi over r. So that means your minus and your minus are going to cancel. So you have a positive term here. And now that means you have a 4 pi over r. So that's 4 pi over r. And then just that original integral of the electric field. So that gives you the first term. And then minus, now here comes the second minus. The second minus from the integral of g, right? Because we did g prime was 4 pi over r squared. We're integrating that. We pick up another minus. So the minus becomes a plus. And now here we take the derivative of that integral, which just means the derivative of an integral is just whatever you're integrating. And now you have a single integral on the left with a row of r, and another integral on the right with a row of r. And now you have a sum of two integrals, and you'll get exactly the same expression from the book. Right, so let me be super clear. Our f is this part. Might as well use colors. So that's your f. And then your g, we use this part. That's g prime, of course, with the minus. Okay, so we're taking f to be this, right? So that means that so we'll get the potential to be, so that first part, so f is this original integral. So that's our integral of r double prime to r double prime, r prime. Oops, see, I'm already messing up. I'm supposed to put the g in front. Okay, so that's minus 4 pi over r with a plus, right? Because that's the g integrated. And then the f is this one, so that's our integral, 0 to R. Now here we need to be careful. So give me a second. R prime squared rho R prime dr prime. Okay, so in the original one, we were integrating from here to there, and then from here to there. But now we were supposed to put as limits of the integral from infinity to, so here it is in R double prime. We were supposed to take these as the limits. So to not zero, hang on, that would be diverging. So to R, yes. So all I did was I copied this whole thing over, and then instead of doing the integral, I wrote down the limits, but I still have the R double prime here. Okay, so that's the first part. The second part, so minus the integral, but now we're going to take the, that's the original integral. It's the original integral, which is the integral from infinity down to R of dr prime prime. That's the original integral, but now we are taking still the G integrated. So there's a 4 pi over R double prime, but it's not a squared anymore. It's so that's where the plus goes. And then so that's the first part. So that's your, yes, okay. And now we're going to take the thing that we were supposed to be integrating. So R prime squared rho R prime. But then after integration, this would be a function of R double prime only. So that means that this thing is now only R double prime. So this is 4 pi over R double prime. R. It's R because we are taking it from infinity to R. So that's R. Now the integral here is still, but instead of, because we're taking these as the boundaries, so that becomes R. And now we have an R prime squared, R prime dr prime. Okay, so that's our first term. And now plus, this should be also a 4 pi, but now we have the integral dr double prime. And now we have an R double prime, but now we no longer have the square here. And because those two cancel. And I believe then we are home. I think all we need to do is relabel some of those R's primes. Okay, so let's talk about the uniqueness of the general solutions to the field. So in general, if you have, and we talked about this before, if you have some kind of a vector field, then you can always decompose that into a curl component and a gradient component. So let's say we have some kind of a field that is some kind of an arbitrary field. So V is arbitrary, and we're not. Right now, we're not limiting it to certain geometrical things like what we were doing earlier, where we were saying the charge distribution needs to vanish at infinity. So we're not doing that just yet, but we will need that in a little bit. So we have this arbitrary field, and then if we take the divergence, oops, sorry, where's my eraser? The divergence of that field, we're going to call that our scalar part, and then we're going to take the curl of that field and we're going to call that the vector part. And now the uniqueness statement is that that these two fields completely specify that vector field V. In other words, we cannot make any changes to V without also changing F and W, right? So so the uniqueness says that F, this is a vector field, F of R and our W of R completely define, oops, define V. So that's the statement that we will check, right? So how unique is that decomposition? So so let's say we have so we're doing a proof through demonstrating that the opposite cannot be true. So so assume that we have there are two solutions. So some V1 and a V2 that both behave according to that equation, that both behave like F and W. So in other words, there is a the divergence of V1 is the divergence of V2, and they're both F of R. And the curl of V1 is equal to the curl of V2, and they're both equal to that same vector field W. And then the question is, can these V1 and V2 be different? So let's introduce a new vector field. So we'll call this V prime, and it's basically the difference, V1 minus V2. So now our uniqueness criterion becomes, we need to demonstrate that given these conditions, that this thing necessarily has to be zero. Okay, so so first, if this is a if this is the difference, then we can write the divergence of that V prime as the divergence of, well, by definition, so that's our V1 minus our V2. So that's our divergence of V1 minus the divergence of V2. And that has to be zero because we said that even though the V's might be different, they will give you the same F, right? So that's zero. And we could do the same thing with the curl. You know, you would just do the same decomposition and you would find the difference between the two W's, but the two W's are not the same. So in other words, that is your zero vector. Okay, now if that is the case, then because it's got no curl, right? We can actually write our our vector field V prime, which is that difference between the two possible solutions between the two possible solutions to the set of equations. So we can write it as the gradient of some scalar different potential. That's supposed to be a psi. I apologize. Hang on, let me make that a little bit nicer. So that's scalar potential, right? And because it's curl free, we can do that. And if that's the case, then we also know that is then the divergence of that v prime. So that's 0, right? So the Laplacian of that difference field is 0, and this is 0 because of this statement. Okay. Now let's talk about the Green's identities. Okay, so I'm putting this right here where we're going to need it. So we'll have some kind of a volume integral and some function f1, and then the Laplacian of f2. And then that's the dot product of the gradient of f2. Yes, I believe I got that. And then we're integrating that over all of space. And that is equal to not all of space, all of v. That's equal to the surface integral of the flux of this f1, oops, not fi, with multiplied by the gradient of f2, and then projected on the normal pointing out. Okay, so that's one of Green's identities. So let's see what happens if we use we'll use f1 is f2 is that scalar difference potential. Okay, so then we will get our volume integral. So that's our psi. Okay, plus the, now this is the gradient of psi, but dotted again with the gradient of psi. So that's the gradient of psi squared. And then we still need to integrate this over all of that volume. And now that's equal to, well, the right-hand side. So that's our delta V. So we'll have here a psi ds vector. Okay, now now we need to start making a couple of approximations. So we'll say that we'll assume that V goes to 0 as least as fast as 1 over r squared. Okay, remember, I was going to tell you that we were going to do that. All right, so what does that mean for this set of equations? Well, first of all, this one is 0 because here we have that 0, so this one disappears. This is the one that we want to pay attention to. Now we need to think about what's happening here. So if v goes to 0 at least as fast as 1 over r squared, then that means that the gradient of that difference potential must do the same thing, right? So v prime is the difference between v1 and v2, but if v1 and v2 are both satisfying that criterion, then certainly the difference should do the same. So that means that this one also goes at least like 1 over r squared. And then, oh, sorry, wrong arrow. This one also goes at least as 1 over r squared. And because this is the gradient of psi, and psi itself has to be 1 order higher or lower, depending on whether you honor the minus signs, right? So this whole thing is going to go at least as fast as 1 over r cubed. Now, that is towards infinity. So we're going to take the limit. So we're going to take the limit where the volume basically becomes as big as the universe. You'll see that this thing we're integrating over is going to go to 0 faster, or at least as fast as 1 over r cubed. But we're integrating that over a surface area, and the surface area goes like r squared. So that means that the right-hand side goes to 0. So our right-hand side goes to 0. And that implies, therefore, that the left-hand side also goes to 0. Now, the left-hand side is the volume integral of the difference scalar potential integrated over all of that same volume. But this difference of the scalar potential is actually it's actually the gradient of the scalar potential is the original v prime. So that is let's do it here, v prime squared v3x. Okay, now this thing is either 0 or bigger than 0, right? Because it's basically the magnitude squared. So this volume integral can only be 0 if v is identically 0. Right? So this is 0 if v prime is 0. And if v prime is 0, that means that v1 and v2 are identical. So therefore, once we have specified the divergence of this field as having this scalar f, and the gradient, not gradient, and the curl of that field gives you this vector field, that is uniquely defining our fields v. So now let's see if we can invert it. So we need to do a little bit of work. So so remember that when you have remember when you have the Laplacian of 1 over r, then because this is like the scalar potential of a point charge, the Laplacian needs to be equal to rho, and this is for a point charge, so that means rho. So therefore, that needs to be equal to minus 4 pi delta r, right? So we don't need to re-show that. We actually went through this whole exercise as showing that this necessarily needs to be true, right? So we're using the fact that we know how this works for a potential as number 1 here. Okay, so we know number 1. That also means that we can rewrite this of 1 over, let's call it r minus r prime, the 3D version, minus 4 pi delta r minus r prime. Okay. So that's our first version. Now, if we take the if we take the Fourier transform of this entire thing, so this is our Fourier transform. We're going to take this entire Fourier transform. Then we have the Nabla operator twice, and we know that every time you have a Nabla operator, you can pull it out of your Fourier transform and pick up a factor ik. So we'll pick up a factor ik squared here, and then we'll end up with the Fourier transform of 1 over r. Okay, on the left-hand side. So we're taking the Fourier transform of this entire thing. And the Fourier transform of the delta function is just 1. Okay, so we'll end up with a minus 4 pi because the Fourier transform of the delta function is 1. We have a minus here, we have a minus there. So therefore, the Fourier transform of 1 over r is actually 4 pi over k squared. So that's quite nice, the fact that we didn't really actually have to calculate the Fourier transform, we were able to figure this out with this straightforward identity and the way that Nabla operators work under Fourier transforms. So yeah, we will, because we're out of time for class today, we'll finish this. Inversion of the problem we were just doing on next class.